So, can everyone see that okay? Great. Wonderful. So, today I want to talk to you about stat solvers, but before we do that, I want to briefly touch on NP-complete problems. So, NP-complete problems are decision problems, which means the solution to them is a yes or a no. And these solutions, when they exist, can be verified quickly in polynomial time. But we don't currently know how to solve them in polynomial time, or in fact, if they can be solved at all in polynomial time. And this is the P versus NP problem, which has come up a few times so far at this conference. So all NP complete problems can be expressed in terms of each other. So they're all equivalent in a sense. So some examples of these NP complete problems are the knapsack problem, traveling salesman problem, so on and so forth, including Sudoku and the Boolean satisfiability problem. So the Boolean satisfiability problem is the question of, given some propositional logic formula, can we assign true or false values to each of the variables such that the overall formula holds or is satisfied? And it's commonly expressed in this form, where these clauses are joined together by ands, and each clause consists of a bunch of literals that are ORed together. So it's a bunch of ORs ANDed together. And this is known as conjunctive normal form. And as I mentioned, this is NP-complete, which means that it can express any other NP-complete problem. And finally, I can tell you what a stat solver is. Stat solvers are programs that solve Boolean satisfiability problems and tell you satisfying assignments. So for an example, let's look at Sudoku. I'm sure most of you have seen a Sudoku before, but just in case, this is what one looks like. The rules are pretty straightforward. So in a Sudoku, especially the kind that we solve on paper, there's one digit per cell, and each digit occurs once per row and once per column and once per grid. And whatever solution you come up with has to use the cells that are already filled in. You can't like change those. So the insight that you need in order to solve these as a Boolean satisfiability problem is that you can use 9 Boolean variables for each cell. So one variable represents whether or not the cell is a 1, second variable represents whether or not it's a 2, so on and so forth. And of these, only one can be true, and the other 8 are false. And then given this insight, you can go ahead and just encode all your all the rules that I told you about earlier as clauses, as Boolean clauses. So here's the rule that every cell has to have at least one value. Each row has all values, and you can do a similar thing for each column. And each cell has at most one value, which means that for each pair of possible values, one of them must be false. So then you can, given that, this is how you solve a Sudoku or any other Boolean satisfiability problem, is that first, you express your problem as a propositional logic formula in conjunctive normal form. 2, you feed it a stat solver. 3, magic happens. And 4, you get a result. And that's amazing, right? So how does it do this? One way is called DPLL. And to illustrate how it works, let's work through a quick example together. So here's a simple propositional logic formula, and we don't know X, Y, or Z. So we start by picking a variable. Let's set Z to false. And then we can do what's called unit propagation. So in unit propagation, if there is a unary clause, which means a clause with only one literal, we just go ahead and assign it. And then delete all the clauses that are satisfied because they're satisfied. And delete the variable wherever it occurs in a clause that isn't satisfied, because it can no longer contribute to that clause being satisfied. So we just don't care about it anymore. So here's what that looks like. The last clause, a unary clause, is deleted because it's satisfied, and the Z in the first clause is deleted because, again, can't help us. We don't care about it anymore. So let's go and set Y to true, pick a new variable. And now we can delete it from the second and third clauses, but then we end up with a problem because we have a conflict. X and not X are expected to be true, and that doesn't make any sense. So what we do is that we backtrack. We changed our minds about Y, we set it to false. And this is looking a lot nicer. The second, third, and fourth clauses are satisfied, and Y and Z have been both removed from the first one, and we're left with just X. And then we can do the other thing, pure literal elimination, where if there's only one possible value for something, we just go ahead and assign it. So solved. We've solved this propositional logic formula. So this is known as Davis, Putnam, Logman, Loveland, after the authors, and it's essentially naive backtracking search with unit propagation and pure literal elimination. And this works reasonably well for small numbers of clauses, but the downsides are that, one, it finds the same conflict over and over and over again, and when it does find a conflict, it can only go up one level at a time. It can only change one variable at a time. And it has no way of like learning from previous mistakes or like remembering them so it doesn't make the same mistake over and over again. So can we do better and can we learn from our mistakes? We can with the method known as CDCL. So CDCL broadly, at least at the beginning, is very, very similar to DPLL. But we keep track of when we make a decision or when our decision implies something. So implies in the sense is through unit propagation and pure literal elimination. And we keep track of the graph. So we kind of keep track of the implication graph that's created by all of this. So here's a larger example. And we start out and we assign A to false, false to A, which implies D must be true. Then we go ahead and assign true to C, which implies F must be false and J must be true. Then we go ahead and set B to false, which implies I must be true. And then we say that E must be true. And now we have a problem because based on the clauses, we have G and not G. So we have another conflict. Fortunately, because we kept track of the implication graph this time, we can identify the variables responsible, in this case, F, C, and E, and we can take them, negate the values that we assign to them, and say, essentially, what happened here cannot happen again. And then we take the clause that we learned, this is our learned clause, and we stick it on the bottom of our original problem. And then based on the variables that we inspected, we know that we have to go up not just one level, but 2 levels in this case. And this is called backjumping. And that's conflict-driven clause learning. So it's DPLL plus learned clauses and non-chronological backtracking. And in fact, this is the basis of most modern SAT solvers. Okay, let's do a silly one. I'm going to talk to you about SLS. So instead of kind of structured approach where we pick a variable, work churn and pick another variable, what if we just guessed? What if you just generated a random assignment and then you picked a random clause and then in that clause you randomly flipped either like the best variable or some other random variable, and you kept doing that until you either got stuck or you found a solution. And if you got stuck, you just throw the whole thing away, do the same thing over and over again until like you hit a timeout or something like that. So this is a form of stochastic local search, and it's surprisingly effective. The algorithm I just described is called walksat, and this can be done in parallel, which is great, which means you can use like GPUs to do it. And it can use a form of clause learning, but unfortunately, because of its random nature, if it fails, it can't ever prove that something is not satisfiable. Because if it like fails, it could just be because it ran out of time. And the family of stochastic search methods is broadly similar in many ways to this, and like simulated annealing is another like technique that this reminds me of. Okay, so far we've been operating at the level of Boolean formulas, Boolean logic, Boolean variables. So how does that help us solve a problem like this, which is a puzzle where the objective is to assign digits to SEND and MORE such that this is valid mathematically, send plus more equals money. So this is very hard to solve using the techniques that I just described, at least for me, because I can't figure out how to tell the SAT solver that it needs to carry the 1, etc. So essentially to do this correctly, I'd have to teach the SAT solver arithmetic. And fortunately, a bunch of people have already gone ahead and done this. This is called an SMT solver, and these are satisfiability modular theory solvers. So it just means satisfiability plus theories. So a theory is like a theory of bit vectors, a theory of arrays, or a theory of algebraic data types that you can kind of express your problem in terms of. And I think the most well-known example of an SMT solver is called Z3, but others include CVC, Yeezus, Boolector, etc. All right, let's recap. SAT solvers are programs that solve NP-complete problems expressed as Boolean formulas in conjunctive normal form. DPLL is backtracking search with unit propagation and pure literal elimination. CDCL is DPLL extended with learned clauses and non-chronological backtracking. SLS is random guessing with probabilistic variable flipping. And SMT solvers are SAT solvers extended with theories. That's all I have for you today. Here's a bunch of resources, including a lovely talk by Lindsay Cooper. Here are these slides if you would like to look at them again later. Thank you.